All right, it's about that time. Well, good afternoon, everybody. Thank you so much for joining me on this webinar, where I'll be going over 3D Experience Engineer, the design, engineering, and simulation toolkit available to engineers and educators everywhere. In this webinar, I'll be focusing on the simulation tools that is available with this portfolio. Before I get started, a few housekeeping items. Your mics have been muted, so if you have any questions, please type them in the question and answer panel on the GoToMeeting application, and I will get to them towards the end of the webinar. Awesome, let's get going. A little bit about myself. My name is Arun Tharaviyam. Again, I'm a product manager here at GoEngineer. I have supported customers for the last 8 years, onboarding them on our simulation tools that's available in the SolidWorks portfolio. And recently, I've picked up the SIMULIA portfolio as well, where I help customers essentially understand both finite element analysis technology and computational fluid dynamics technology and help them be successful with their projects with them. For this webinar, I have a pretty straightforward agenda. I'll be giving you an overview of the simulation tools that's available with this 3D Experience Engineer bundle, as well as the SolidWorks simulation technology. And I'll be going over some differences between the two solvers that is available from both these product suites. And finally, I have an example that I basically use for all my engineering classes and when I onboard engineers on both FEA and structural analysis to help them get comfortable with the software and get comfortable with the science. Now, when you talk about simulation tools, now we're talking about two different buckets here, or two different suites. There is the SolidWorks suite as well as the 3D Experience suite. It helps to kind of distinguish between the two and kind of figure out what people refer to when they talk about these different names. As I mentioned, when they talk about SolidWorks or 3D Experience, they're referring to a suite of tools. And these suite of tools essentially cover design tools, manufacturing tools, simulation tools, and data management tools. Now, each of these tools essentially has a brand name associated with them. And with SolidWorks, it's simple. They're all called SolidWorks, all the brands. But under 3D Experience, the simulation tools fall under the SIMULIA brand. So anytime you hear the word SIMULIA, either through Google searches or if someone's dropping in conversation, they're essentially referring to a brand of solvers that can be used to essentially validate product design. Now, for this presentation, I'll be specifically focusing on the structural analysis FEA solver. And the name of the FEA solver in SolidWorks is called SolidWorks Simulation, while the 3D Experience SIMULIA portfolio is essentially driven by the ABAQUS solver. So the ABAQUS solver is a world-renowned solver that's existed in the industry for the last 30 years, and it's been used to tackle some really complex structural analysis in various industries. Now, let's kind of unpack SolidWorks simulation because it'll kind of help us put the 3D Experience simulation technology in perspective. Now, why is SolidWorks simulation so popular? It is a very powerful CAD integrated analysis tool. So if you are comfortable with using SolidWorks, learning the simulation product is easy, and hence it's very popular amongst both engineers and students. It uses the finite element method. So basically you discretize your CAD models using the meshing process with either solid elements, shell elements, or beam elements. And then you apply boundary conditions to essentially evaluate your products for strength. Now, the two common analysis types that are available with the SolidWorks simulation suite are static analysis and dynamic structural analysis. And if you want to dive a little deeper, the most popular analysis type that's been used by R&Ds all over is called the linear static analysis. With the linear static analysis, what you basically do is you apply constraints and you apply the environmental loads that a product undergoes. And then you run the analysis to figure out the strength of the product to withstand these loads. So if the strength of the product exceeds this, or if the stress of the product exceeds the strength of the material, then you can justify product failure and you can make modifications to be able to improve the strength of your product. Now, the next class of analysis is the dynamic analysis. In philosophy, it's very similar to the static analysis. The only difference is the type of load. So if you're trying to analyze the strength of a structure in a vibrating environment, we're able to do that with SolidWorks simulation by plugging in time-varying loads to take a look at time-varying responses of these structures. Now, the third analysis type, which is actually very popular in use, but it's not talked about very often, it's called the nonlinear analysis. It basically takes the linear static analysis and applies various degrees of complexity to it. For instance, if you have multiple components that interact and have changing contact areas, or if you have components that undergo excessive deformation, or if you're testing materials that aren't conventionally don't conventionally behave like metals, typically materials like rubbers or metals when they push beyond their yield points, you typically rely on this nonlinear analysis technology to tackle those problems. Now, these three kind of analysis types are just are a part of a bigger suite of simulation tools that's available with SolidWorks Simulation. For instance, we have a fatigue analysis solver that is able to take all your linear static results and basically cycle those loads to look at how your product performs for high cycle fatigue. So that way you're able to predict the life cycle of your product. In addition to that, we have an optimization tool that essentially automates your design exploration process using simulation. So if you're testing a product, a certain dimension of a product, you can plug in those dimensions and plug in boundaries for those dimensions, and the software will essentially sweep through those boundaries to figure out the best combination of dimensions for strength and for typically weight reduction. Now, why I brought this in perspective is, now when you take the 3DEXPERIENCE simulation tools, specifically the ABAQUS solver, it has all of the same tools, but the key differentiator between the SolidWorks simulation tools and the 3DEXPERIENCE SIMULIA tools essentially lies in the nonlinear analysis capability. And like I said, when I talk about nonlinear analysis, I'm talking about multiple components undergoing large deformations, multiple components interacting with changing contact areas, and materials that don't behave as linearly as metals, specifically materials like rubber. So if you take this little bushing here, you can see that it collapses, and it really it behaves a little more elastically than something like steel or aluminum. Now, with that in the backdrop, some key differences between the SolidWorks simulation technology as well as the 3DEXPERIENCE ABAQUS technology are listed here. So basically you can make there are three primary differences. One is the capability of the two solvers, the meshing technology that is available with the two solvers, and finally the workflow, how you set up the analysis with the two. So let's unpack this one by one. Now, when you talk about solver capability, again, I'm going to draw on the nonlinear analysis examples because that's the key differentiator in terms of analysis type. Now, the ABAQUS solver essentially is superior to a lot of the solvers out there in the market, and even SolidWorks simulation when it comes to these areas. So one area is large deformation, specifically when it comes to post-yield or collapsing components or components undergoing buckling. So if you have a scenario like this where you're doing a 3-point bend test where you have some permanent deformation on your component, or if you have a rubber component like this that's collapsing completely, it becomes complicated for a lot of other solvers to tackle that we're able to do with 3DEXPERIENCE. The next area is contact. Again, when you have multiple points of contact and if you have changing contact areas, this solver technology becomes superior. Again, nonlinear materials, as I mentioned before, when you're dealing specifically with rubbers or materials that can essentially undergo large amount of deformation for a small amount of force, this solver becomes becomes really useful and really powerful. And finally, impact. Now, there is a technology or solver technology that's available with the ABAQUS solver in 3DEXPERIENCE called the explicit solver, and the sweet spot of this explicit solver is short duration dynamic events. So if you have drop testing or impact testing or any colliding, any set of components that collide, we have the ability to tackle that with this solver. And everything that I've listed here in parentheses are reasons why a lot of our users essentially use the ABAQUS solver in 3DEXPERIENCE over the inbuilt SolidWorks simulation tools. And that is not to say the SolidWorks simulation tools are inferior by any means. They have their sweet spot and they have a wide variety of applications, but there are fringe applications that our customers need that essentially fall into one or all of these categories where the ABAQUS solver is far more superior. And when you take commercial solvers in the market, right, you can basically group them into a few buckets or two specific buckets based on how convenient they are to use all the way to how capable they are to use. So you have solvers that are very convenient to use in terms of just setting up the analysis, but they may not be as capable. But you have other solvers out there that are extremely capable, but they're not as convenient to set up, and you really need knowledge of both FEA and a lot of training on the software to use. So when you take SolidWorks simulation, it kind of falls in the Goldilocks zone. It's very convenient to use, but it is also power packed to give both engineers and students enough technology to evaluate their product designs. But when you take 3D experience, it also falls in that Goldilocks zone, but I'd say it is far more capable in terms of the type of analysis that it can solve. Now next, meshing. So when you talk about meshing, essentially any analysis solver's claim to fame is the flexibility of meshing tools that is available in the solver. And specifically in this case, I'm going to discuss the difference between the solid meshing capabilities that's available in SOLIDWORKS Simulation as well as 3DEXPERIENCE. Now, when you take solid elements, you have two kinds of elements. You have the hexahedral elements and you have the tetrahedral elements. With the 3DEXPERIENCE ABAQUS solver, we have access to the hexahedral elements. Whereas with the SOLIDWORKS Simulation solver, we have access to only the tetrahedral elements, whereas 3DEXPERIENCE, we have both. Now, why do users need the hexahedral elements? It's been proven time and again for a variety of use cases in industry that the solve speed of a hexahedral of a part that's been meshed with hexahedral elements are way faster than an equivalent tetrahedral mesh. And even when it comes to the quality of results, any component undergoing large deformation or undergoing multiple points of contact, as illustrated in the previous slides, essentially the hexahedral elements are able to produce more accurate results for a larger mesh. Now, why this isn't available in a lot of analysis tools is because applying a hexahedral element to a component it can be quite challenging, especially if a component has complex geometry. So it requires a lot of model preparation, such as splitting and partitioning from the user. In spite of that, there are a lot of companies that still utilize the hexahedral meshing, because if they're able to just partition the component or make the component easy to hex mesh once, they're able to reuse that component and essentially save time on the save time while they're iterating on a design. Now, on the other hand, when you take the tetrahedral elements, why they are available in almost every solver out there is because it is a very robust automated meshing process, or a very robust element that can be incorporated in automated meshers. It's very easy to define areas of interest, and so if you have questions about the validity of the result in a certain area, you can go into that area and increase the mesh density of the tetrahedral elements in that area, which is kind of difficult to do on the hexahedral side. Now, the biggest disadvantage of the TED elements is it is way slower than the hex elements for an equivalent size. But I'd argue that you do not need that speed for every analysis type that you use. You really need solve speeds for a very complicated analysis that could take really hours to solve. So a lot of our customers who are running these analyses that take about an hour or a day to solve are essentially switching to the hexahedral mesh to be able to speed up their solve times and improve the efficiency of their analysis process. Now, I can give you an example, and this was done by one of my colleagues, Sean Bentley. He basically did a drop test of a cube. He took a cube and dropped it from a 5-meter height, and he took a look at how long this model took to solve with hexahedral elements compared to tetrahedral elements. And you can see the solve times for the hex elements are way better than the solve times for the tet elements. So the solve time is almost 1/5 faster than the tet elements. And even when you look at the quality of the results at the point of impact, while the high stress areas are very similar in both cases, the hex elements essentially give you way cleaner results for such a highly dynamic event. Again, kind of driving home the point that that hex elements, it is worthwhile spending time hex meshing your models and taking a look at this technology to improve your solve speed and the quality of your results. Now, the last differentiator I'd say is the workflow between the two products, and I'd like to address a few buckets here. It's not only the workflow bucket, but I'd also like to point out this example that I present to a lot of our engineers to build confidence in the results produced by the FEA solver. Now, this is a typical 3-point bend test setup where you're trying to figure out the structural strength or the flexural strength of a part. So you basically have the part of interest that's between 3 rollers, and you apply a force on one of the rollers, and you take a look at how this component bends, and using that you get feedback on the strength of the product, the elastic modulus, and so on and so forth. Now, another reason why I picked this example was this was kind of difficult to solve in SolidWorks. We had to apply a lot of solver settings, and we had to make a lot of simplifications to be able to get a good result because of the multiple points of contact due to the rollers. But then this was an easy solve with the ABAQUS solver available with 3DEXPERIENCE SIMULIA. So let me kind of jump into the solver interface and show you what the interfaces look like and how you go about setting up the problem. So unlike SolidWorks Simulation, the 3DEXPERIENCE simulation solvers are in a separate application, but there is a connector that connects these the components in the simulation environment to the CAD environment in SolidWorks, and I'll talk about that a little later. So this is pseudo integrated. Although the simulation model is disconnected from the SolidWorks model, it is connected. It is technically connected with the SolidWorks connector. Now, when you take a look at the simulation environment, you'll notice a couple of things. One is a feature tree here that essentially gives you access to all the analysis items that you've set up. You have the command manager here, or the action bar here, that essentially gives you all the items to set up the analysis. And you have this handy assistant panel that helps you keep track of the stage of the analysis you're in to make sure that you've completed all the stages to be able to run the analysis. So if there are any errors in your setup, it's immediately indicated by the assistant and you can make corrections accordingly. Now, as I mentioned, you interact with this little action bar to set up multiple things. You essentially specify the analysis type, and then after you specify the analysis type, you can jump directly into the measure. Now, as far as the measure goes, you have a lot of choices with this program. And as I mentioned, for solid elements, you have two key choices. One is the tetrahedron measure and the hex measure. Now, since this geometry isn't complicated, it's basically swept or extruded, we can utilize some of the automated hex meshing capabilities. So that saves you time on model prep. So for instance, when I select this body, the software is automatically recognizing the swept directions, and I'm able to apply the hex mesh, with, like I said, without too much model prep. Now I have control over the number of layers and the local mesh size. So if I want to improve the quality of my results, I'm able to do that right away by just manipulating those numbers. In the same fashion, I'm able to apply this sweep hex measure to the rollers as well. Again, manipulating the mesh size and the number of layers to each of these rollers. Now, one tip here is you don't need to refine these rollers as much because they're going to be a material that's stiffer than the block of interest. So you can apply a relatively larger mesh size to these rollers compared to the block. Now, another thing I want to point out is connections is a very handy feature here in the 3DEXPERIENCE simulation program, where you can essentially apply a coupling to the roller that you're going to apply the force to. The benefit of this coupling is it creates a point that you can directly apply the force, and the force applied to that point is transferred to the face of interest. Now, once that's complete, once you've completed the mesh and once you've applied the connection, you can move on to the next stage where you're essentially defining the interaction between these components. And the benefit of this, the ABAQUS solver, is we have access to something called general contact. Now, general contact enables you to automatically apply contacts to all surfaces in the components without having to manually select all the surfaces. So clicking this button, the solver will automatically recognize the contacts during the solve process, simplifying the workflow for engineers from having to identify every contact face and manually define them in the software. Now, this is a big benefit, especially if you have components that are collapsing onto themselves and you really don't know which faces should come into contact. Now, once I've kind of flipped the general contact button, you can go ahead and investigate the tree to make sure that the general contact essentially has showed up under your interactions. And once you've made sure that it showed up in your interactions, you can go ahead to the next stage. The next stage of the setup would involve applying loads and boundary conditions. And the nice thing here is that you'll be applying them directly to the non-meshed elements. So that way, if you do make a modification to the model, the loads stay attached to the original face. And once you remesh the process, you remesh the model, the software essentially applies the the load to the newly remeshed face. Now, since I want to apply a 50 Newton load in the negative y direction, I'm able to apply that directly to that coupling element. And as far as the boundary conditions go, if I want to fix both these rollers, I can pick a clamp constraint and again interact with just the geometry in order to complete that setup. Now, this should kind of give you an idea of the bulk of the setup. What I'm going to do is I'm going to jump to a tab that has the analysis results already loaded. So this is another nice thing about the interface. It's that you're able to keep multiple tabs open with multiple simulation setups, and you're able to jump between one and the other to essentially investigate multiple different analysis. Now here I have the stress results, the maximum principal stress results loaded, and I'm able to essentially use this probe tool to kind of take a look at the max stress. Well, the chart essentially indicates the max stress, but I'm able to locate it right away by using this little analysis probe. So this is the target number that I want to take a look at, which is 3.47 megapascal. So I want to look at this number for two reasons. One reason being I'll be showing you how I analytically validated this result. And the second reason being, hey, I want to make sure that I don't apply so much force that it actually breaks the component that I'm studying. Now, besides the stress results, I'm able to take a look at even the displacement results. And this is another benchmark that I can do, where I can compare the displacement results from the analysis software and validate it analytically. That's another reason why I chose this model. It is complex in the sense that the setup is, you have multiple points of contact, but it's easy because the geometry is predictable and you can quickly hand calculate these results to validate the analysis results. Now, I'm going to jump back into my presentation to kind of go over the analytical validation. So we ran the analysis, we kind of took a look at the deformation. Now, when it comes to analytical validation, you basically need two really simple equations. One is a beam bending equation, or the bending stress equation, which requires just the moment applied at the point of interest, the neutral axis, and the area moment of inertia. Very easy to calculate for a simple shape like this, and the stress ended up being around 3.75 megapascals, while if you remember, the stress obtained from the simulation was around 3.47 megapascals. In the same fashion, we can use the beam deflection equations to kind of figure out the deflection due to the applied load, because this is a simply supported beam, and the standard formula for that is FL cubed by 48 EI. Plug in all of the values, and you basically get a deflection of around 2 millimeters. Again, comparing these to the results obtained from the solver, you can see that we are really close. The error is less than 10%, which is pretty acceptable in the simulation field. Now, you can kind of improve the simulation. Now, you need to appreciate the fact that, hey, when you actually run these hand calculations, you're not taking into account the geometry of these rollers. So there'll definitely be a small discrepancy between the stress obtained from the simulation and the stress obtained from the hand calculations. Now, we can actually set up this model without these rollers and rerun the analysis. And I've actually done that, and you get you get results that are very close to that 3.75 megapascal mark. You have an error that's less than 1%. Again, the reason I didn't do that is because I want to illustrate the contact capability with the solver, that even if you start stacking complexity, that the ABAQUS solver is able to handle those scenarios. Now, one last thing I'd like to point out in the workflow is the CAD update. Again, with SOLIDWORKS, you're very accustomed to modifying the model on the fly and rerunning the analysis. But how does that work with 3DEXPERIENCE simulation? Now, here, what I want to do is I want to make a small change to the indenter. I'll reduce the width of the indenter from 25 millimeters to 10 millimeters, and I'll do this all in SOLIDWORKS. And as I mentioned, we have this little connector panel that you can use to push this change to the simulation environment. Now, once I hit save, what the software is doing, it's modifying the model in the simulation environment. And once the modification is complete, the panel essentially indicates that through all of these green check marks that you see on there. Now, after the modification, I'm going to go back into the sim environment. There are multiple ways you can update the simulation model. The easiest way I found is just reloading the simulation, reloading the simulation file. And there's a little update button you can hit, which is about to come up right here. Yep, once you hit that little update button, you're able to, the software updates the mesh to the newly updated, the new geometry. and all the boundary conditions are mapped to the new geometry as well. So that's kind of how the integration works, and this is another reason why this is very popular amongst the SolidWorks, or amongst users who primarily use SolidWorks as their CAD tool of interest. It's because of this connected workflow. Now, to summarize what I went through, in the last couple of slides, now we discussed two different analysis technologies, one from SolidWorks Simulation and one from 3DEXPERIENCE. The 3DEXPERIENCE role or software that's available, simulation software, is called Durability and Mechanics Engineer, and the app is called Structural Mechanics Engineer. Again, the sweet spot of both these solvers is to be able to run linear, static, and dynamic loading. But what really differentiates the 3DEXPERIENCE solver is the ABAQUS technology that's able to do some really complex nonlinear analysis involving contact, large deformation, and nonlinear materials. Now, structural analysis isn't the only simulation technology that's available on 3DEXPERIENCE. We also have a CF computational fluid dynamics tool called Fluid Dynamics Engineer. And on the SolidWorks side, we have an integrated simulation tool called Flow Simulation. Again, the sweet spot of both of these tools is to be able to run internal analysis, like this manifold, this exhaust manifold that you see on my slide. External flow analysis, where you're doing aerodynamic validations or hydrodynamic validations, and also heat transfer analysis, where you have all three forms of heat transfer that we're able to simulate with CFD. So that involves conduction, convection, as well as radiation. Now, to summarize our discussion, again, why do we need two different solvers? Yeah, SolidWorks Simulation is great. It's a very easy tool to use, and it helps you understand FEA and illustrate FEA to a large audience. But there are some advanced technologies that people need to be savvy about that the 3DEXPERIENCE solvers can essentially introduce to everyone. This helps students and engineers be prepared for industry, where they can be thrown the different simulation technologies, and really getting exposure to the 3DEXPERIENCE side of things gives you, helps them be more adaptable and gives them exposure to those advanced technologies. And the analytical validation example that I showed you is just one of several examples that I demonstrate to people to build confidence between the FEA solver and the analytical results. But then this can essentially be used to help drive home the point that FEA is an accurate technique, and it's a good way to validate products, and it's a proven technique to validate products. And finally, the big motivator to use the simulation products under both these portfolios is that they're completely integrated with SolidWorks. So if SolidWorks is your design tool of choice, it's very easy to make a transition to the simulation environment with either of these technologies. And with that, I conclude my presentation. Again, thank you so much for listening. If you have any questions, please type them in the question and answer panel, and I'll be happy to answer them for you.